Okay, welcome everybody to day 2. So yesterday, Jesse explained the dictionary between statistical physics and learning theory. So we've talked the talk, and now it's time to walk the walk and see how to use that language as a sort of guiding principle to say some interesting things, some non-trivial things about learning machines. So this is a slide from yesterday. Just to remind you, thermodynamics says the world is organized by phases and phase transitions. Geometrically, that means singularities and unfoldings. And singular learning theory connects both to learning machines. This is also a slide from last time. So I said that we were going to introduce the free energy formula and show you how to do some interesting things with it. So the first part of today's lecture is introducing the free energy formula. We've encountered it sort of implicitly a number of times, but I'll explain precisely what the free energy formula statement is. There'll be a few more references this time than last time. Gray book, green book, we've seen. Here's a reference to what we tend to call the WBIC paper from 2013 and the renormalizability paper, which is another very important paper in the history of SLT, but maybe you wouldn't notice unless you were very assiduous about looking at the references in the green book. So this kind of set up the next step of the theory, which is what's contained in the green book. And this is a talk that Watanabe gave. He's given the talk again this year, but he gave it a couple of years ago, I think. I forget the exact date, which is where he lays out a story about phase transitions in the data set size. So far, that hasn't been published anywhere. So I will be following that for part of today. So here's the outline. I'll introduce the free energy formula. I'll talk about model selection as coarse graining. So that's the kind of physics view on model selection in statistics. I'll talk about internal model selection. I'll talk about coffee. It's never a mistake to make coffee. So the setup for today is that x1 through xn are independently subject to the true distribution qx. The model is px given w, and phi is the prior, w is the parameter space. In the case of neural networks, we're interested in sort of estimating a conditional dependence. I'll get to that in a moment. The log loss or negative log likelihood also was introduced yesterday. So that's lnw as minus the average of the log of the probability of each data sample given the model W. The Bayes free energy is defined to be the negative logarithm of the integral of that quantity, the product. I'm not going to say too much about why this is the right quantity right now. Jesse said a little bit about it yesterday. It will come up as the right quantity in a moment. So for now, this is just a definition. All right, so this is the partition function under the integral. So it's negative log of the partition function. And if you just examine the definition, right, if you take e to the minus n ln w, then you'll see that this is the same thing as that. Okay, so depending on the situation, we tend to write it in one of these two ways. So to put neural networks or really any regression model into this framework, we assume the true distribution is given by such a product, and that the model is also factorized in that way, such that we're not estimating the true distribution on the inputs, right? So that's not our problem. Phi is our prior, as I said, and we're going to suppose given samples, but now our samples are pairs of inputs and outputs. Inputs are X, outputs are Y. So this is the model, Gaussian distribution on the Y's, given the X's. fxw is the neural network with weights W. In this case, ln, the negative log likelihood or log loss, is just the mean squared error up to some constants. So you do a little calculation, the logarithm of the exponential, you get the mean squared error, and some term which is the empirical entropy of the true distribution on the inputs, which is just changing. I mean, if we think about this as energy, as Jesse was saying yesterday, then these terms here are just changing the 0 point of the energy, and we don't care. Okay, so I'm just going to leave out these terms. I mean, mostly I'll just be talking about lnw as a kind of as the central object, You're free to think about that as being mean squared error and ignore those terms. It's not important for our purposes. Okay, so here are the ingredients. LNW. Much of what I'm going to say is not tied specifically to this particular model or neural networks, but you can keep that example in mind if you like. These are the different ways of presenting the free energy. So as I said, negative log the partition function. The partition function is this integral. And the Bayesian posterior, the probability of a parameter given a data set, is this ratio. So 1 over the partition function, e to the minus n lnw. Okay, so those are the formal players. Here's the precise statement of the free energy formula. So we're going to then give some more friendly statements, but I'll start with a precise statement. It's actually not like completely trivial to, like this isn't like just stated clearly with all the hypotheses, because somehow Watanabe is working in the green book with like ambient hypotheses from the gray book and so on. So you have to piece together the green book, the gray book, and maybe also the renormalizability paper. But here's the statement. So under some conditions, I'll come back to those in a moment, the free energy as defined is NLNW0. I'll say what that is in a sec, plus lambda log n. And then there's the log n term, a random variable, FRN, and Fn converges in probability to this sum here. So that's what the OP1 term means. Okay, so what's W0? I'm not saying, it's up here, yeah. Okay, so W0 is a point that minimizes L. L is the average over the data set of Ln, or the large n limit of Ln. So think of W0 as being the closest you can get to having a true parameter. So here's an important difference with the setting in which Edmund was speaking yesterday, which was under the hypothesis of realizability. So we're not assuming that. That's important for the discussion of phases. We're not assuming that there is a parameter for which the model actually gives the true distribution. Okay. We can, however, talk about parameters that get as close as possible. That is, parameters which minimize L, or what's the same, minimize K, the KL divergence. And that's what W0 is meant to be. There may be many of them, but let W0 be one. There's a condition which I'm not going to put up here because it's a bit of a tangent to explain what it means. Relative finite variance, you can see the green book. So this is a significant weakening of the hypothesis. One way of thinking about it is it's a weakening of the hypothesis of realizability. So it allows for the theorems to work even in the unrealizable case, provided you have this, which maybe you could think of as a kind of very relaxed form of convexity or something like that. Okay, so under this condition, and then you add to that the fundamental conditions of the gray book, accepting realizability. And this point, there needs to be a point minimizing L, which is in the interior of W. I'm not actually sure that that's necessary, but that's the way the theory is currently written. So I'm going to put it there. Okay, and then the theorem says that we have this asymptotic expansion for the free energy, where lambda for the moment is just a positive rational number, the learning coefficient. We'll interpret that as the RLCT later. M is the multiplicity. I'm not going to explain what that means. It's just some integer greater than or equal to 1. And as I said, FNR is a random variable, which converges to a random variable in law. So if I take the expectation over the data set, so this is a random variable depending on the data set dn. If I take the expectation over that, this is stochastic. It depends on the data set through the ln. W0 here is a minimum of L, but ln, so then we put ln in the formula. If I take the expectation over the data set, this becomes deterministic, and that becomes just a constant. Okay, so you can read that as order n, order log n, order log n, and a constant. Okay, so that's the free energy formula. This random variable FRN, you can think of that as hiding all the lower order terms, and those are not well understood yet. Okay. So the friendly statement is to just drop off the FR and say that this is O log n, right? So the first two terms, the n ln W0 and the lambda log n term. Mostly, I guess, are what we care about, although we'll see later these constant terms or lower order terms do matter. So this is the really friendly statement. Just think about that as a constant. Okay, or think about it as 0, which I'm going to do for a lot of this talk. And here's the secret. Log n is 3. Okay, I hope Watanabe never watches this lecture. But look at that. That's 10 to the 9, guys. Log n is 3. Okay, like for any experiment you'll ever do, log n is 3. This is a constant term. Okay.
No, I have a question.
Yeah.
How big is M? You know.
M, yeah, that's true. Yeah, we don't really have a good handle on M. Yeah. So that's right. It's not appearing on its own. It has a coefficient. This was in front of the log n. Yeah. Yeah.
Usually unique one. But where does its multiplicity come from? Does M?
Yeah, I don't really want to get into that right now.
Right.
That sort of requires introducing the resolution and essential coordinates. Okay, so it's n ln W0 plus lambda log n plus some constant, more or less. Okay, so what is free energy? Okay, so that's the formula for it. But why do we introduce the free energy? So for a statistician, you would say it's the basis of model selection. So let me go through a bit of how the statistician would introduce model selection. So we suppose given a true distribution, QX, and a data set DN, and then we have two models which are competing for our attention. One with parameter space W1, one with parameter space W2, models P1, P2. Okay, so how are we to decide which is a better model? Well, the story goes, if you're a good Bayesian, then you should write down the probability of the data set Dn for the model 1, which is this integral, right? It just follows from Bayes' rule, do a little calculation. So the integral over W1 of that product gives the probability of the data set according to that model. And then you should prefer the model which assigns a larger probability to the data set. That's the idea. Okay, but whoops. If I take that quantity and I take a negative logarithm, well, log is increasing, so that negative logarithm is a decreasing function. So that will be greater than that if and only if this is less than this. So we want to prefer the model with the lowest free energy. Did I say that around the right way? No, I think I didn't. Okay, so we would prefer the model P1 if P1 dn were greater. P1 dn will be greater if FNW1 is less. Okay, good. Okay. Okay, so I'm going to write FNW1 to mean the free energy of the model. I mean, really, the model is not just the parameter space, but you'll forgive me. So FNW1 means the free energy of the first model. So we should prefer the model with the lowest free energy. That's what the man says. Yeah.
So I notice we use model class condition. Is this confusing for some people?
Oh, yeah, I saw that comment. Yeah. Yeah, so by model, I mean picking a particular parameter. So when I say model, I mean parameter or distribution parameterized that is according to a parameter. Oh, and here I'm saying model. Yeah, that's right. Okay, that's just a mistake. Yeah, this should say model class 1 or yeah, learning machine 1 or something. Yeah. Thanks. Right, so the man says that we should prefer the model with the lowest free energy or the highest model evidence. This is like one of those places coming to statistics from the outside that I think many mathematicians are like, why do I have to do what you tell me to do? Maybe I'll choose the other one just to spite you. Okay, so the reason this seems a little odd, I think, when it's, at least when I first saw this, is that some of these exist completely in different universes, right? Like they're just completely separate things. Like, why should I even believe these numbers can be compared, right? So we can get around this by, this is also a pretty standard trick. We can just say, well, they're actually not separate model classes. I can just think of them as one model class in a very formal way. I just take the model class, which is the disjoint union of the parameter sets. Now, you might say, formally in singular learning theory, we want this to be a subset of R to the D, so these would have to be the same dimension. But this, I'm speaking much more abstractly than that, so don't worry about that. It's not important. So we take the disjoint union of the two parameter spaces, and I take the model, which is defined conditionally. So P behaves like P1 if I take a parameter that belongs to the first model class, and like P2 in the second model class. Okay. Now they're not different model classes, they're different parts of a single model class, just formally. All right. So what is the free energy of this disjoint union of the two models? Well, it's the negative logarithm of that integral. And that integral just splits up as an integral over W1 and W2. Oh, this is a mistake. This should be P. Okay. The P1 in the integral should just be P. So when I'm integrating over W1, I get P1. So you'll believe I get this, or rather, the summand here will be e to the minus this, right? Because if I rearrange this formula, I get the integral is e to the minus the free energy. So this is negative log of the sum of those two exponentials. Okay. Now, if you remember log sum exp, if you take a logarithm of a sum of exponentials, that's pretty close to just taking the maximum of the exponents. Okay, so if we look at that expression, we can sort of see the model selection principle from the previous slide. But I want to go a little bit further than that. Okay, so I'm going to write FNW alpha. Alpha is now going to index the model classes. So alpha is 1 or 2. So that's just the formula from last time. And let's do Bayes' rule again. Let's say, what is the probability of model alpha? You could just say probability of alpha given dn, perhaps. Well, by Bayes' rule, that's the probability of the data set given the choice of model class alpha times the probability of model class alpha, the prior probability divided by P of dn. Now, this P of dn refers to like P of dn for the disjoint union. But this here is just P alpha. So this term here is e to the minus FNW alpha, just because it's just coming from here. PW alpha, I'm just going to write as phi alpha, capital Phi now. You could think of that as a meta prior over the different choices of model class. And PDN, well, if you think about it, it's got to be the denominator. So it has to be the sum over all available model classes, in this case indexed by beta, of the numerator, e to the minus FNW beta phi beta. Okay. So that's what we could call the model evidence in context, where you see the alternatives. I mean, that's the kind of weird thing maybe about model evidence presented as such, is that you just compute this probability and then like in some other universe, there's another model and it delivers a number to you and you're supposed to respect that number. Well, if we put them all into a big model, then we compare them by Bayes' rule, and that's the form. Yeah, as I said, so Fn of W, the overall free energy is just negative log the sum of e to the minus FNW. Okay, so what we've arrived at is we've basically discovered coarse graining. So coarse graining is an idea in physics, a very important idea, which rests on, you could call it a kind of symmetry, perhaps the most fundamental symmetry in statistical physics, arguably, which is the symmetry of changing your mind about units or length scale. And actually it came up in Jesse's talk where it was someone asked, how do you decide what microstates are? Right? And actually, this is a very fundamental question. Like, you don't know what a microstate is, meat bag with a microscope, right? Like, you think it's velocities and you think it's positions and momenta, but well, what about gravitational degrees of freedom? What about whatever's inside those particles? Like, you've just decided somewhere in this enormous hierarchy of scales to say microstate, but there's actually nothing fundamental about that. You could have gone down or you could have gone up. But the macroscopic physics doesn't care how you've decided to define microstate, right? And observing that fact and sort of systematically developing it mathematically was one of the greatest breakthroughs of 20th century physics. Okay, so here we're doing a very primitive version of that. But what we've done is we've gone from, in the language of the statistical physics lecture from yesterday, we talked about parameters as microstates. So let's just stick in the first column to get our bearings. So the fine-grained, like the language we were using up until now, was that parameters are microstates. The microscopic energy, a kind of stochastic Hamiltonian, is this quantity, which is the exponent in the posterior, which is associated to that parameter. So that the Boltzmann distribution, if you want to think about the posterior as a Boltzmann distribution, then it's this term here. And the partition function is the integral over all parameters. But notice that we have two Boltzmann distributions because we had two model classes. And the free energy is defined to be in this relationship to the partition function, right? It's e to the minus fnw alpha. Okay, so, well, we just computed the model evidence, right? For model selection, we're just statisticians. We've got two models, model classes, and we want to decide which one to pick. And then the second step is within that model class, maybe to pick a parameter by the kind of procedures that Edmund was speaking about yesterday. We formulated that choice, that model selection process, as being governed by something that looks itself like a Boltzmann distribution, right? So then we should look at that exponent and think, okay, well, maybe that's an energy of something. What is the index? Right, in the Boltzmann distribution, the sum in the denominator is over states, right? So this is an integral, but in any case, the microstates are the things that we integrate over in the Boltzmann distribution, right? So in the case of the fine-grained story, the states were parameters. That's what we integrate over. We've discovered that model selection is governed by its own integral, but the index is beta, the model classes. Okay, so forget about there being two model classes. Let's suppose there's a million of them, right? There's just some number of possible model classes competing, and they're indexed by alpha. And, well, according to this, we should follow the logic of saying, in this new coarse-grained Boltzmann distribution, the microstate is the model class, identified with its index alpha. The microscopic energy is whatever goes in the exponent in the Boltzmann distribution. So that's the free energy of that model class minus log of this meta prior. The Boltzmann distribution is just the thing given by e to the minus that. And then I have a new partition function, which is the denominator in that Boltzmann distribution. And I'm going to denote that with a fractor f. Okay, so that's f sub n. This is all at some fixed data set size n, right? There's a fixed data set dn behind all of this. Okay, well, nobody stopped us from doing that. Where have we arrived? We've arrived at the idea that just following Bayes' rule, model selection has to be governed by the coarse-grained Boltzmann distribution, where the free energy is the new microscopic Hamiltonian for the model index alpha. Yeah.
By model selection, do you now mean model class selection?
Yeah, like maybe I'm rebelling against my instructions. I don't know, I'm just going to say model selection. I mean, it's the term that's used. I don't know. I'm not going to switch to some new terminology. I agree it's a bit confusing, but I'm not going to be able to stick to it. But yeah, I do mean model class selection. That's right. So if you like, you can think about that as what the free energy is. Right? The free energy is the coarse-grained energy. So the coarse graining here is at the level of, if I go back to one of my pictures. So what is the coarse graining? I'm replacing this entire, so this is a whole space of parameters. I'm just going to zoom out so that that looks like one point to me. And if I were to zoom out and think of it as one point, what energy should I associate to it? So the idea in coarse graining is that you should pick an energy for the coarse grained thing such that the dynamics that sort of is associated to that energy is as close a reflection as possible to the microscopic dynamics. And that's the logic is basically what I just presented. Okay, so that's one way of thinking about the free energy. It's the coarse-grained energy, or coarse-grained negative log likelihood. Now, if the differences in free energy of the model classes are sufficiently large, then that log sum x argument means you just select the model with the lowest free energy. But they're competing in that logarithm, right? So in the logarithm, the free energy, the overall free energy was a logarithm of a sum of two exponentials. And if they're similar in size, then the model you select might switch from one to the other. And that's basically the story of phase transitions that I'll come to in a moment. Yeah.
The second bullet point that you just showed.
Yeah.
The maximum likelihood estimation applied in coarse graining.
Yeah, that's right. Yeah, that makes sense. Yeah, and as within a single model class, there's differences between maximum likelihood estimation and other things you might do. That's right. Yeah. Okay. Nobody stops us from continuing, obviously, right? Coarse grain again and again. We'll stop here though. Yeah, I want to focus on this coarse-grained free energy, the Fn, for a moment. Oh, sorry, I'm pointing at Zn, right? I said this incorrectly before. I apologize. Bad choice of. It's math frac Z. That's my sophisticated take on the alphabet there. Okay, so I said this incorrectly before. That's Zn, right? The coarse-grained partition function, because of the denominator in that. So the coarse-grained free energy is negative log of that. That's negative log of the sum of the possible model classes of e to the minus model class free energy. And as I said, that's basically for sufficient, as long as there's enough model classes, that's very close to being minus the maximum of the exponents, which is the minimum of the free energies over the model classes.
Wait, we dropped the phi's, right?
Oh, I did. Yeah, thank you. Yeah, I did drop the phi's. Yeah. So I'm assuming here that the phi's are just all equal, for example. Yeah. Yeah, I just got sick of writing the phi's, but the phi's are there. That's right. Okay. So the point I want to make here is that computing the free energy at the coarse-grained level is performing roughly looking over all possible model classes for the minimum of their free energies. Okay, so the coarse-grained free energy approximately minimizes the free energy over the available models. Now, this is all very abstract, and you might say, well, model selection is something statisticians do. Is that really actually fundamental? Now, partly the point I want to make is that actually you shouldn't think about it as something that people do. So this is like Bayes' rule says you should do this. And that means that at least according to, if things are governed by the Boltzmann distribution in the posterior, then as I'll explain over the next part of this talk, this happens automatically in Bayesian learning, internally to a single model, and especially if the model is large. Now, the conditions under which this happens are not well understood, but it seems pretty reasonable to expect that in a very large neural network, for example, that this principle is actually quite significant. That in a large neural network, learning, at least to the degree it's like Bayesian learning, is strongly dominated by this principle of internal model selection, where you take the story I just said, but think about it as living inside a fixed parameter space. And I'll explain what I mean. Okay, so this is a sort of first definition of phases and phase transitions. It's vague because I'm not saying exactly what I mean by internal model selection, but here's the idea. So suppose we have a fixed model PQ phi with parameter space W, and that for some reason, there are some particular subsets of parameter space such that computing the free energy of the model W looks like what I just described as a minimum over free energies of sort of submodels. To the degree that's the case, the internal model selection process will choose some particular submodel in a way that depends on the data set and hyperparameters. And those possible choices I'm going to refer to as phases. And a change in the data set size or hyperparameters which causes that choice to be different is a phase transition. Okay, so that was kind of where we're heading to. Now let me explain precisely the sense in which you can view that model selection story, that coarse graining, as happening internally to a single model. So now there's not model classes, there's just a single model. Yeah, I'm not really spelling that out on the slides, I'm sorry. So for the rest, we're fixing a single model, okay, PQ phi W. And we're looking inside that model. Okay, so this is sort of half spelled out in the talk of Watanabes that I mentioned earlier. There's some technical requirements for this argument to go through. I'll just briefly say what they are, since this argument's not published anywhere, but I don't want to dwell too much on the conditions. You can ask me later. So I'm going to suppose that there is a finite collection of compact sets. Think of them as like these hypercubes, which cover W. Where each W alpha sort of could stand as a model in SLT on its own. So there's a long list of conditions it needs to satisfy, but just to spell out some of them, it should be semi-analytic, that is cut out by inequalities using analytic functions, have a non-empty interior. Now this means it contains a non-empty open set in R to the D, right? So it's not lower dimensional. So these are, in the picture, these are sitting inside R3 and they're three-dimensional objects themselves, right? Has a non-empty interior and contains in its interior a point that minimizes the average log loss LW on W alpha. And we assume relative finite variance so that we get the free energy formula. And well, I said they cover W, but actually what I want is something a bit stronger. I want to assume that every point lies in the interior of some W alpha. So it's not that like you have two cubes touching on a face and that's the only cubes that the things on the face are contained in, right? There has to be some cube such that you're actually in the cube. Okay, so then you take a partition of unity subordinate, roughly speaking, to that cover. So pick an open cover of W with the property. So basically take every point. It's in the interior of some W alpha, pick an open neighborhood that's contained in W alpha, take those over every point, compact by compactness. You can do that with finitely many. And U alpha gamma is going to be an open set which is contained in W alpha. And then I'm going to take a partition of unity subordinate to that cover. And then I just mess with the prior so that the prior multiplies with that partition of unity. Okay.
So what's the partition of unity subordinate?
What is it? So it's just a collection of smooth functions which locally there's only finitely many things. So it's just a collection of smooth functions taking values in 0, 1, such that at every point the functions add up to 1. Thanks. Okay, so here's a little calculation you can do. Fn is the free energy of W. That's the definition. Negative log integral over W. Once I have a partition of unity, I can split that integral into a sum over these subsets, alpha. And then I look at this integral and I think to myself that this is just the partition function for the W alpha model. So W alpha can be thought of as a model in its own right, where the parameter space is W alpha, it's a compact semi-analytic set. The prior is now phi alpha, the same model P, just restricted. The truth is the same as before. So this is a model class. This is a triple in its own right, and that is its partition function. So it's e to the minus fn W alpha, where this is the free energy of that model, that restricted model, that submodel. Okay. So I can apply the free energy formula to that submodel, and it says, here I'm taking the friendly version, so I'm calling the OP log n term C alpha. All the subscripts here refer to the fact that this depends on the choice of submodel, right? So this is a point in the interior of W alpha that minimizes L. I'll call it W alpha star, so it's a point of lowest energy. Lambda alpha is the learning coefficient of model W alpha, C alpha. I'm thinking about it as some constant. Okay, so here's internal model selection. This is why it works, right? Because the integral I just did shows you that the free energy of W is approximately, for the reasons I sketched earlier, the minimum over all the available submodels of the free energy of that submodel, which means, and that's just completely formal, this first line, right? Just this integral partition of unity argument that I did earlier. It's basically useless unless you have an expression for the free energy, which the free energy formula gives us. Okay, so this, if you like, is the main thing you want to take away from this talk. I mean, the free energy formula, obviously, plus internal model selection. This idea that if you're just doing Bayesian learning in a fixed model, somehow there might like automatically be appearing a process of internal model selection governed by some subsets and their energy and complexity. So the argument here is the Bayesian posterior selects phases, the alphas index phases, on the basis of competition between energy. Right? So if I'm minimizing this over alpha, then in that minimization, there's competition between the energy of each phase, the complexity of each phase, and then the subleading terms. Now, we don't really understand much about those subleading terms. That's one of the most important open theoretical directions in SLT, I would say. But in particular, we know that's where the prior goes. So if you look at the derivation of the free energy formula in the asymptotics, there's no mention of the prior here. That's because in the asymptotics, the prior gets buried into this stochastic term. So that stochastic term is where the prior enters into the behavior of the free energy. I'll say a bit more about that later today and also on Friday, but it's not well understood, but very interesting. Okay, so we have the free energy formula, we have the principle of internal model selection, and now is the promise of doing thermodynamics. So up until now, it's kind of technical.
So very quick interruption, just the previous slide. Yeah. Is this lambda with the real canonical threshold?
It's the real low canonical threshold of this restricted model. Yeah. So you could think of it as measuring the singularity of the level set where L is equal to W alpha star.
Right, and it's also a measure of the simplicity sort of.
That's right.
Of the model. Okay, yeah.
Yeah. Okay, so now that was the technical background. Now I'm going to switch gears and do thermodynamics. So this is now a black box. We have this internal model selection principle, and we have the free energy formula. And I'm going to make some simplifying assumptions. I'm going to replace this stochastic thing by its deterministic version, L of W alpha star. This is justified by some of the theorems in the Green Book in terms of the relation of the asymptotic expansions of the quenched free energy and this one. I don't want to go into that. So both theoretically, and if you look at experiments, like this is often for the range of n's you're considering quite stable already relative to the size of the other terms. So this is reasonable. Not always, obviously, but this isn't crazy. And to start with, I'm going to assume that the subleading term is not contributing. Okay, so I'm just going to take, I'm going to write E alpha to be the energy of the phase alpha. So that's just L of W alpha star. And lambda alpha is the learning coefficient, or RLCT, of that phase. Now I'm calling it a phase, but like from a physical point of view, it doesn't really deserve the name phase until it sort of actually appears in connection with dynamics. So many of these subsets, I mean, you can choose these subsets in stupid ways so that a given subset just never appears because it's never the minimum of the free energy for any values of the involved parameters. Or you could choose it too close to another phase so that in practice they're not distinct phases. So that's all. I mean, there's like a whole, it's like a whole story here, only partly worked out, but roughly speaking, this, we'll just call the alphas phases. So in the following story, Greek letters are going to stand for phases, and we're just going to explore what this internal model selection principle means. Starting with phase transitions. So I described earlier that we were going to take a model, the possible submodels that would appear in the internal model selection, we would call phases. A phase transition is where we vary the n, the size of the data set, or some other hyperparameter that's just missing here that determines like maybe there's a hyperparameter in the truth. So we'll talk about that example tomorrow. Liam will. So maybe there's some hyperparameter that is also sitting inside the model. If varying n or varying a hyperparameter changes which alpha is the minimum. Right, so no. So at a fixed n and fixed hyperparameters, we perform this minimization over alpha. So then the minimum alpha is a function of n and those choices, right? So a change in those, in the n or the hyperparameters, which causes alpha to change, is a phase transition. Okay, so what do we know about phases? Well, they're characterized by their energy and their complexity. So if you have two phases, alpha and beta, where beta has lower energy, remember we're minimizing, right? So lower energy wins. Like if your energy is lower and your learning coefficient is lower, then you just win for all values of n and all values of the hyperparameter. Right? Because, well, this is an increasing function of energy, and that's an increasing function of RLCT, right? So if you have both lower energy and lower RLCT, you have lower free energy and you win. Okay, so if a phase alpha is dominated by beta, both in energy and in learning coefficient, then the free energy of beta is always lower than the free energy of alpha, and there can never be a phase transition from alpha to beta or reverse, right? It's just, there's no change in the hyperparameters or n that can, a phase transition would mean that for some values of n, it's one way, for example, and for some values of n, it's the other way, right? That would be a phase transition. So for there to be a phase transition n from alpha to beta, and this is increasing n on this graph, right? For there to be a phase transition from alpha to beta, the phase alpha would have to be preferred for low n. That means its free energy would have to be lower. And the reverse would have to be true for high n. And therefore, somewhere in between, they'd have to be equal, except n is an integer. So maybe they're not exactly, right? If you thought about n as continuous, then they would have to be equal somewhere. If that happens, if this relationship between the free energies as a function of n holds, then we call the n at which it happens the critical data set size. And as I said, I mean, the critical data set size is a formal object. It could not be an integer. But the closest n would be like moving through that integers near that value, you would experience a phase transition. I'm going to talk about only phase transitions in n today, just to simplify matters. But much of what I'm saying also applies to hyperparameters, some of which may actually be continuous.
I have a question.
Yeah.
So yeah, you mentioned like the critical data set size might not exactly be an integer or something. But like also like throughout this discussion, we're assuming a deterministic L,
Yeah,
which is not exactly true, right?
Yeah.
So is it just the case that the noise and
That's right. That's right.
Okay.
Yeah, that's right. Yeah. So I mean, the presence of noise here is actually quite is going to be important in the development formally of the theory, because the size of the noise will determine whether two phases are really distinct or not. So you could have two phases that are really quite close in energy and entropy. And for the ranges of n for which they're actually preferred, the noise may be sufficient that they're not actually well-separated phases, so that they're actually one phase. But clarifying that depends on understanding better the stochastic fluctuation. Yeah,
I think this is similar to the finite size effects. This is going to
yeah, I think so. Yeah, but yeah, it's not. So this is like the singular fluctuation that actually Xiaowei was talking about yesterday is related to this. I don't really understand how you clearly related. Okay, I'm mentioning something about screening there, simply because you could have this relationship, but still never see, like, to say there's a phase transition is to say that at some value of n, this is the minimum free energy, right? Like this is the actual chosen phase. And then it switches to that being the actual chosen phase. Now, we could have this relationship, but somehow, like this is not the chosen phase at this time, and that's not the chosen phase at that time. Like they're just crossing somewhere high on the graph and nobody cares. Like the system's just completely ignoring those phases. Or it might be that during this crossing, actually some other phase becomes dominant in between. Okay, so that would sort of correspond to this arrow factoring through some gamma, right? So really when we're talking about phase transitions, we're sort of meaning like really consecutive things, minimal steps where it's actually dominated by alpha, and then at the critical data set size it's dominated by beta. But I won't say anything about screening. Okay, so now let's do some thermodynamics, right? Let's do some algebra. Now I said that if these inequalities both go the same way, then there's nothing to say, right? If E beta is less than E alpha and lambda beta is less than lambda alpha, or the reverse, that is with alpha and beta switched, there's no phase transition. So without loss of generality, just pick one of them to be the lowest energy, and then the RLCT, the learning coefficients, go in the opposite way. Okay, so where is this critical data set size? Well, just put the free energy formulas equal to one another and solve for, and this is positive by hypothesis, and solve for n on log n. And we get that n on log n is minus the difference of the learning coefficients divided by the difference of the energies. N is, well, we're taking this greater than 1, right? So the function n on log n is positive and increasing. So this has a unique solution, right? Provided this number is positive, but these choices make positive. And that's the critical data set size. Okay, so there's a picture. So here the orange line is the free energy of phase beta. E beta is less than E alpha. Eventually, I mean, n dominates in the asymptotic, right? So for very large n, the ordering is determined by the first two terms, not the first terms of both of the free energies. So for sufficiently large n, it has to be that the free energy of the phase beta is less. Then it's possible, when this happens, that for low n, the log n term dominates, and that's what's happening here. Right? So the lower learning coefficient phase is dominant for small n. And the critical data set size, they cross. Okay, so where is that crossing? Well, we're just solving n log n critical on log n critical equal to negative delta lambda on delta E. My convention in these slides for delta lambda is that it's sort of like directional, right? So you're going from phase alpha to phase beta. So delta alpha, if we go back, that's why I wrote it this way here. You take the learning coefficient of the target phase minus the learning coefficient of the domain source phase. So lambda beta minus lambda alpha, and E beta minus E alpha. So that's the numerator there is delta lambda. So delta lambda is positive and delta E is negative. Okay, so that's
yeah.
Yeah.
Just can I just translating this again out into from the physics talk into like just statistics. So my understanding is that you're making this transition from alpha to beta, and alpha is a simpler model, but beta is like better, fits the data better if you have more data.
Yeah, I'll say exactly that in a moment. Yeah, that's right.
Right, okay.
Yeah, so what we're seeing here is, I'll just repeat for the audience. So what Alexander was saying is that if you look at this graph, what it's saying is that for large n, the free energy, Bayesian model selection, internal model selection, is going to prefer the phase that has lower energy, which in the regression case means lower loss, right? It's a better fit. But when n is small, you see that what's preferred is the other phase, which has more error, but is simpler. Right? Learning coefficient is a measure of complexity. Okay, so this picture here tells you that what the phase transition represents in terms of sort of an information or learning process is that you're switching from preferring a solution which is dumb but simple to preferring a solution that is better but more complicated. Yeah.
So like if I think about this in the statistics context, right? Normally, like this kind of thing would make sense when there are like a small number of simple models. There are tons of complex models, right? So you want to start with like one of the simple ones because there are so many you choose from that are complicated. Is this going to be true of the lambdas? Because like as of right now, I know very, very little about what lambda alpha and lambda beta actually are.
I'm not quite sure I understand the question. What is going to be true of the lambda?
There are only a small number of phases.
Oh, I see. With
With-
small lambda.
With small lambda, yeah.
Yeah, so just to repeat the question. So in normal statistics, you might imagine there's a small number of solutions with low complexity and many solutions with high complexity. Yeah, I don't know that I have anything to say about that. But it's kind of a question about phase structure, about which I guess I don't know anything. Yeah, I mean, you're sort of asking for a general argument, I suppose, for like why there can be more ways to be complex than simple or something. Yeah, it's a fine intuition. I don't know. Yeah. Okay, so here's
Maybe another question.
Yeah. Yeah.
So going back, we take the negative log, and that lets us use this approximation to the max with the log exponential. Why use the negative log is the question.
The approximation to the maximum is just the logarithm. It's not negative anything. So
Right.
Yeah. So it's not really a question about choosing to use the logarithm. It's just the model selection is based on free energy, and that has a logarithm in it. So I'm not choosing to put the logarithm in.
So why is it based on free energy rather than just the partition?
Oh, I guess you could say it is. Oh, I see. Okay. So in some sense, the way I said it was that the minus logarithm is just a decreasing function. And so we get to equivalently think about it as either prefer model evidence, which is what you're saying, prefer the partition function, or prefer minimizing free energy. But they're the same thing. So it's not a choice. Yeah. So I think when Keynote crashed, I might have lost the last few slides. We'll see. So I'm just noticing there's a difference to what I had in the latest bit. Okay, so this is the observation we've made, that assuming that E alpha is greater than E beta, lambda alpha is less than lambda beta, there's a candidate phase transition from alpha to beta. Candidate merely because of this screening phenomena. So I'm not going to care too much about that. There could be a phase transition from alpha to beta. At the critical data set size, which is this curly n, is just the inverse to n on log n. So for n greater than E, this is an increasing function. Take its inverse. I'll call that curly n. So the critical data set size is curly n of negative delta lambda on delta E. you might recognize this is to do with the latent heat in thermodynamics. I won't go any further into that analogy, but this is not a quantity that is unusual in thermodynamics. What I'm doing here is like bog standard thermodynamics, by the way. Set the free energy equal, derive some equations. Okay, this is not anything clever that I'm doing here. This is just what you do in thermodynamics once you have a fundamental relation. Okay, this is interesting, right? Like just by simple formal manipulations and algebra, we derived this observation that phase transitions in N that change the energy must decrease the energy and increase the learning coefficient. Okay, the first makes sense, right? As you're learning, you're decreasing the error. But the second is not an obvious observation. And in fact, I think it's counterintuitive for a lot of people. And we just talked about what's happening there, but the learning coefficient increases over the process of learning. And that might seem like you want to choose a low learning coefficient, right, to minimize the free energy. But you're not choosing the RLCT or learning coefficient independently. You have to choose it jointly with the energy. And that means that phase transitions will tend to increase energy at the decrease energy at the same time as increasing the learning coefficient. And what that looks like is information getting pumped into the model, right, from the data. So you start off with a model that is complex. You start off increasing the learning coefficient is increasing its complexity, right? You start off with a model that's very simple, like the hypothesis that the function you're trying to understand is just zero or constant. As you're seeing more data samples, you're starting to fit better to the data by pumping information into the model, which is increasing its complexity, right? The number of bits necessary to specify the parameter. Yeah. Okay, so informally, the learning process produces more accurate models that are more complex, sacrificing extra bits in the model description for fewer errors. Now, we might ask about phase transitions that don't change the energy. But are there any questions about this part?
We have a question about the noise going down.
Yep.
So first, is anything known about the nature of the noise? We're talking about the
well, the noise is a continuous transformation of the random variable xi, the empirical process xi, which is statements about that are made in the grade book. Yeah, so we know something about that xi on the resolution. And then you apply some continuous transformation to it, and that produces this FRN. Beyond that, I don't know. That's right. Yeah, one of the main theorems says something about that noise. Yeah, yeah. In this context, like how to cash out that description in some useful way, I don't know anything beyond the formal statements. Understanding this noise better is certainly one of the most important theoretical directions in SLT, and very closely linked to applications in connection with phase transitions. So yeah, this is an important open direction. Okay, so this seems like it might be a bit in the weeds, but actually this is like really quite remarkable. What if the energies are equal, right? And that might seem quite strange, like it seems odd in physics to sort of maybe talk exactly about equal energy unless there's a symmetry reason why there might be a degenerate energy level. But there is a degenerate energy level in at least one of them in SLT that we could think about, which is the set of true parameters, right? Those are the set of true parameters or the set of optimal parameters. Those all have the same energy. So what happens at the end of learning when you've actually found a true parameter? Do the phase transitions stop? Well, let's have a look. So let's consider the case where, sorry for the small font. Consider the case where the energies of two phases are equal. Oh yeah, I'm going to stick the subleading terms back in now. They were ignored before, okay, because they didn't really matter too much. You might think, sort of generally. some examples, like what we'll see on Friday, even for low n, these subleading terms seem like they can have an impact. But generically, sort of they're subleading terms. So you sort of should perform the analysis, ignoring them to begin with. But now when the energies are equal, well, the difference in free energies has lost its first order term. So it makes sense to bring in the subleading term, because that's what's going to compete now with the learning coefficient. Okay, if the energies are equal and the subleading terms are equal, then there's no transition. If you have a look, the free energies being equal mean the RLCTs have to be equal. So basically they're the same phase, at least as far as free energy is concerned. Okay, so to have a transition, we have to have, at equal energy, we have to have the subleading terms different without loss of generality. Let's suppose C alpha is larger. And the free energies being equal, well, put those two things equal to each other, rearrange, and you see that negative delta C on delta lambda is equal to log n. That has a solution if and only if the left-hand side is positive, which is if and only if lambda beta is greater. And when that happens, the critical n at which it happens is e to the minus delta C on delta lambda. Okay, so here's what this looks like. At equal energy, with C alpha greater than C beta, I'm not telling you what these subleading terms mean. Like, this is like a measure of complexity. I'm not giving you an interpretation for those because I don't know one. Okay, there's just some subleading term. It takes some value. What I'm about to say will give you maybe a first piece of knowledge I have about what this subleading term means. Okay, so if C alpha is greater than C beta and lambda beta is greater than lambda alpha, then there is a transition, or there could be, from beta to alpha. Why have I written it that way? I'm not sure. I was saying alpha to beta before. It's a bit confusing. Hope I got the direction correct. Yeah, that's right. That's, well, then we can check the graph to see if I'm making sense. Okay, so this is lower order than this. So for large n, the log n term dominates, and the thing with lower lambda alpha should be dominant. Yes, and it's possible that at low n, the thing which you could still dominate even though lambda beta is greater, the lower free energy dominates, right? So I'm looking at the lower envelope of this. This is free energy. It's a function of n. So this is a transition from beta to alpha. Yeah, okay. Okay, so you see here that there's before it was a competition between the first order term and the second order term, and now it's a competition between the second order term and the lower order term. Okay, so here's, this is what I said before. This is the first observation that we had. Here's the second observation. We just derived. Phase transitions in n that do not change the energy must decrease the learning coefficient, right, from beta to alpha. Must decrease the learning coefficient and increase the subleading term. This is opposite in terms of its effect on the learning coefficient to what happened before. So we've now discovered two different kinds of phase transitions. One is in n. One is a phase transition that decreases the energy and increases the learning coefficient. That's information going into the model. The model is becoming more complex. And another is a phase transition that decreases the learning coefficient, makes the model simpler. The trade-off is that it increases this subleading term. Okay, so once the learning process reaches the set of optimal parameters, this is, I mean, we could imagine this happening in any level set, but most interestingly, this is true for the minimal energy level set, a set of optimal parameters or true parameters in the case of realizable models. Once the learning process reaches that set, so this is like for very large n, say, it starts to undergo transitions that lower model complexity. So this is a very non-trivial prediction about Bayesian learning that you can derive from this like high school algebra once you have the free energy formula. Okay, and Edmund knows that graph, yeah.
So you give physical interpretations interpretations of what this was. All right, so you give a interpretation of what this energy means and what this learning parameter means. You also have something similar for this for these lower order terms. Sorry, higher order terms.
No clue.
All right.
Definitely want to know. I don't know. Yeah, I mean, the multiplicity is there in the log n term. That's true. I guess, right, I'm sort of presuming that it's not actually the multiplicity that's changing. It could be, yeah, but I guess I'm sort of thinking it's a prior related effect or some other thing. Yeah.
So, observation 2.
Yep.
Assuming you're able to perform some large amounts of computation faster than n is increasing, general learning will start with a very complex model, a random model, maxed out RLCT, and then if we're lucky with enough computation, find a simple model. So we're assuming that the process happens faster than you're increasing n. Is it true that we start with a complex model?
Yeah, I wouldn't.
Gaussian initialization, take out a simple model.
Yeah, I wouldn't agree with the premise of the question. Yeah. Yeah, it's a reasonable question. I don't have beyond just kind of saying I don't think that actually the initial, well, of course you can choose the initial parameter to be high complexity. So maybe then there would be yeah.
We are talking about Bayesian learning here. So either there's no initial.
You don't get to choose, yeah.
There's no initial
Right.
parameters and there is no process of learning. But if you are to realize Bayesian as a process of learning, for example, using MCMC or some other approximation to sampling on the posterior, then yes, there is a large number of computers for that.
Yeah. But I mean, Matt's saying that you could choose the prior to be Gaussian at the origin, in which case for low n, that's going to be, not too different from the posterior. So it's a reasonable question. Yeah, I'll have to think about that, Matt. Are there any other questions? Okay. Okay, so here's a picture of the behavior of the learning coefficient as a function of n that we've arrived at. And that might seem strange because we're used to talking about the learning coefficient as a global thing, right? Like the whole model has a learning coefficient, which is the largest pole of the zeta function for the entire model. That's this lambda. That's global lambda. That's the destiny of lambda, right? For extremely large n, it must be the case that the RLCT or learning coefficient of the phases that you're looking at must become the global lambda. Okay. That isn't necessarily the lowest lambda of any phase, nor the highest lambda of any phase. It's just some learning coefficient, right? But that's what we usually mean by the RLCT, is this global RLCT. But we've been talking now about lambda alphas. So when I say lambda n, what I mean is the following complicated thing. I say, at data set size n, look at the posterior, see which phase alpha it prefers, and take lambda alpha, the effective learning coefficient at that data set size. That's lambda n. And what I've just described to you is a simple model that predicts this non-trivial behavior of that learning coefficient, right? The learning coefficient, the effective learning coefficient at data size n should increase with decreasing model error until some point. This is where you hit optimal parameters or true parameters, right? Exactly here. And then it should start to decrease and sort of asymptote to the true RLCT. And actually, you see this in experiments, right? So you do MCMC, you estimate learning coefficients, and you see whoop, things exactly like this. Edmund has experiments with MNIST where you see exactly this shape. This comes up over and over, and we'll see it also in the toy models case. So this you see in experiments. This is real. Sorry? Oh, this is in the unrealizable case.
You would then They're true.
Oh, so this means the RLCT of an optimal parameter.
Just all.
On the optimal set, take the lowest RLCT. Yeah. Okay, so this is our first non-trivial fact derived from just doing thermodynamics, right? With the free energy formula and internal model selection. But I have some more. Yep.
You think this explains wrong?
Yeah, it's tempting to say so, yeah. I don't know. But it's very similar in some sense to the storyline of grokking, right? Where you have memorization and then the model switches, learning seems to switch into another phase, which is sort of pumping out entropy from the parameter to simplify the solution. Yeah, so just to repeat the question. So the story in grokking, I'm not saying this is an explanation of grokking, but there are some similarities between the explanations that have been put forward for the storyline of grokking and what I'm saying here. So the storyline is that at the beginning, you're just trying to get low error. So maybe you're memorizing lots of junk, right? You're just going all out to reduce error. And you're pumping all sorts of ad hoc information and so on into your model. So the RLCT, the complexity is increasing. Then at some point, you've wrung every last drop out of the first order term in the asymptotic, right? And then you switch to the second order term in the asymptotic. So now you're going to wring every drop out of the learning coefficient at the cost of increasing whatever there's other things, right? You're dumping all your rubbish into the third order term, but who cares? You're decreasing the RLCT.
It seems like it would come from the prior, from the regularization.
Yeah, that's right. So yeah, so it's interesting that rocking and also double descent seem to have a strong influence from weight decay, right? That's consistent with the story as well. So because the weight decay would affect exactly the prior term. So if you were to look at this story and imagine where weight decay or weight regularization plays a role, it is in the third order term, the subleading. So there being some sort of tension between the capability of the model to pump out entropy from the true parameter, well, the optimal parameter. This would be harder if you're fighting against a smaller term in the subleading term. So
okay, so still some confusion about this figure. So should it be monotonic for the transitions with the screen?
up until this point, yes, good question. Yeah. So the critical ends have to increase, right? Yeah, so I'm going to come back to the screening. That's a very good question. Maybe this will do. Okay, so here's N critical. If you've got a transition from alpha to beta and then to gamma, the N critical for the beta gamma transition has to be larger than the alpha beta one. See? N is the inverse of an increasing function, so it's increasing itself. Okay, so for N critical for beta to gamma to be larger from the transition from alpha to beta, you need some relationship. I mean, this quantity needs to be increasing, right? So that's got to do with, skip this slide. So otherwise it would be screen, but the screening has a different, I mean, the screening depends on this number here. So the screening, what happens with screening switches also at the transition point, exactly because now the formula for the free energy has switched once you go to this case with the equal energies. So it's a good question, but no, the screening behavior is not dictated by that past this point. Was there another one? Or that's it? Okay. So let's talk about generalization error. So the generalization error, I mean, there's actually 4 of them. I'm going to talk about the Bayes generalization error and the expectation of that over the data set. That's affected by phase transitions. Well, more precisely, this is a function of n, right? The Bayes generalization error at data set size n. That's, well, Jesse defined it as the n derivative of the free energy, which is fine. The n derivative of the free energy, of course, depends on what the free energy is at n. And if it's governed by phase alpha, then it looks like the n derivative of f, the free energy of phase alpha. Another way to say it is that the Bayesian generalization error is the KL divergence between the predictive distribution and the truth, and the predictive distribution is an integral against the posterior, and the posterior is concentrated in the current phase for a given n. So the generalization error will look more or less like, except at phase transitions, away from phase transitions, it will look like the generalization error for the dominant phase. Okay, so that's the sense in which this is affected by phase transitions. At a given n, this looks like the generalization error for phase, the dominant phase of that n. Okay, so let's look to see where the graph of generalization error crosses. That is, where the graph, so this is the n derivative of the free energy formula, right? Should have it up somewhere. So the n derivative of this is E alpha plus lambda alpha on log on n. Right? Yeah, so we haven't really talked enough about generalization error. I apologize for that. That's a bit of a coordination problem with these lectures. But, so the generalization error looks like this as a function of n. Given n, so where would the generalization error graph for phase alpha cross or phase beta? Well, you solve the equation, you see that it's the same figure as before, but now n is equal to that. Before it was n on log n is equal to that. Okay, so the high level story here is that the free energy curves do not cross at the same place as the generalization error curves for the different phases. They can either cross before or they can cross after. And then we can ask the question, which one is it? Like given a phase transition, is the generalization error lagging? It sort of switches after the free energy switches, or does it switch before? And again, we can do a little bit of algebra and see that it's almost always going to be one way and not the other. Yeah, sort of running out of time, so maybe I'll go through this a little bit quickly. Okay, there's like some little elementary algebra that tells you that transitions are almost always standard, which means that a transition from phase alpha to beta will be such that the generalization error for beta will be lower than that of alpha at the transition. And I'll just show you a graph of what that looks like. And this whole hour and a half is basically unpacking figure 7.6 in the great book. Section 7.6 is probably the most interesting section of the book outside the proofs, but it's a little bit cryptic. And basically what I've been explaining is sort of the story of this diagram. So let me show you some actual graphs that reproduce that diagram. So that section of the book is called the singular learning process. So here's an example. Here's the phase transition from earlier, same graph from alpha, the chosen phase, lowest free energy, to beta. And this is the graph of the following numbers. So energy of alpha is 0.15, energy of beta is 0.05, lambda alpha and lambda beta have those given values. These are pretty close to the values in the toy models of the superposition example. That's sort of why I was playing with these particular values. So we'll see exactly these curves or things very close to them on Friday again in an example. So what's delta E? It's the change in the energy across the phase transition. It's negative 0.1. The change in the RLCT is positive, it's 4. So negative delta lambda on delta E is 40. And the N critical is about 215. Okay. So let me just flip backwards and forwards. Same x-axis, more or less, all right, N. The vertical axis is free energy in this case, generalization error in this case. So here you see the generalization error for the first phase, the dominant phase for low N. And so this is where the free energy switches, right? So for N to the left of this, alpha is the dominant phase. The blue line is the actual generalization error of the model, EBGN. And you see that before N critical, it looks like the generalization error for the dominant phase alpha. After N critical, it looks like the generalization error for the dominant phase beta. And there's this kind of S curve. That's the phase transition, right? That's a signature of the phase transition in the generalization error, one of the derivatives of the free energy. Now, it's actually like, in some sense, jumping instantly, you might say. But if you look at, not really, because if you look at the formula, it's like it's this log sum exp thing, right? So it's kind of switching rapidly at N critical. This is where they're actually equal, the curves. The generalization errors cross before the transition. Okay, and the little bit of algebra here shows that basically this is all that this is what always happens. If the competition is only between the energy and the complexity, then you will always see this ordering where the generalization errors cross before the free energies do. And that's another simple little bit of algebra.
The slope of the transition happening.
The slope of the transition. That would be asking for another derivative. No. Yeah, I mean, it's, well, I mean, if you think about this as being second order derivative of the free energy, then you're taking a third order derivative of the free energy. So, yeah. Yeah, well done, Alexander. Gold star. Okay, in 2 minutes, here's a dummy's theory of scaling laws based on a kind of similar story. So the point here is that, so I've talked about how internal model selection works, that assumes some set of phases, alpha. The set of phases determines which phase transitions are possible. The relationship between the phases is dictated by the energy, the learning coefficient, and the subleading term. Right? Okay, so phase structure means the set of possible phases and the relationship between them indicated by those values. Right? So let's examine the simplest possible model of those phase structures, assuming that there's a large number of phases, which I'm going to index by positive integers, in such a way that transitions go from alpha to alpha plus 1. So this is like a simple model of the story that's consistent with the laws I was mentioning earlier, right? That energy must decrease, lambda increases, and so on. Okay, so I'm going to assume that for lambda less than alpha, the energy, so that means there's going to be a transition from alpha to beta potentially. So E beta must be less than E alpha, lambda beta greater than lambda alpha. I'm not going to model this long-term behavior for very large n, where the subleading term starts to matter. I'm just talking here about the first kind of phase transition. So for these to be unscreened, we have to have that the critical data set size is an increasing function of alpha. And here's the simplest model I can think of in which that's true. Take E alpha to be decreasing, take it to be 1 over alpha, and take lambda alpha to just be alpha, it's an increasing function. Then delta lambda across the transition is just not A. I had this in my head, a more general thing before. It's 1. Okay, so delta lambda is 1, alpha plus 1 minus alpha, and delta E is minus 1 on alpha, alpha plus 1. So that means minus delta alpha on delta E is alpha, alpha plus 1, which is positive. And an increasing function of alpha. Therefore, n of it is an increasing function of alpha. So this is a series, an infinite series of unscreened transitions. Okay, so that's the phase structure. So let's compute the dominant phase as a function of n. So given n, the phase which is dominant is the argmin of alpha of ne alpha plus lambda alpha log n. Alpha is a discrete index, but that won't stop us because we have our physicist hats on. So dd alpha it is. So set 0 equal to dd alpha. So we get minus n on alpha squared plus log n. That means n on log n is alpha squared. So solving that, we get alpha n is root n on log n. Okay. That is the dominant phase at data set size n. Okay, so we have this series of phase transitions. What happens to the generalization error as a consequence of all these phase transitions? Well, EBGN is the generalization error for phase alpha, the dominant phase at data set size n. So that's E alpha n plus lambda alpha n on n. So that's 1 on alpha plus, yeah, that's right? Lambda alpha on n. So that's root log n on n plus 1 on n, root n on log n, factor out the log n on n. And this term here is quite small relative to 1 for large n, right? So this approximately just looks like log n on n to the power half. Okay, so what is this saying? It's saying that if you have a model, a very large model, which can play host to a very large number, effectively infinite from our point of view of phases, with decreasing energy and increasing complexity, then there's an effective learning curve. So this graph of generalization error against n is sometimes called the learning curve. There's an effective learning curve, which doesn't look like, I mean, if the learning curves in singular learning theory look like minimum value of L plus RLCT on n, right? They have a scaling exponent of -1, like lambda on n. But when you have lots of phase transitions and a sort of continuous phase structure, the effective learning curve can look more like something with an exponent of -0.5 rather than -1. Now, it's not exactly -0.5 because it's a log n. Okay, but this is fairly close to being n to the -0.5. Okay, so there's an effective learning curve which is a different exponent to the one that the theory says. Okay, so this is a hint that even though the theory will predict always learning coefficients, learning scaling exponents of -1, there can be effective exponents which are different to that. And the effective exponent is a function of the phase structure. If you change the phase structure, if you change the way that lambda increases, you change this to alpha squared, for example, then you'll change this exponent. Okay, I'm not saying this is an explanation of the scaling laws that are observed in transformers. It's just some toy example using the free energy formula and model selection. But it's not ridiculous to think that large models, large neural networks could be host to many, many phases, enough that you can effectively consider them as maybe continuous, and that therefore the learning curve for such large models is dictated by some kind of emergent learning curve along these lines. Now, if we understood the phase structure of large transformers better, then maybe this would go some way towards explaining scaling laws. But right now, we don't understand that at all. Okay, so to summarize, the promise that was made about connecting SLT to thermodynamics was that this would actually give us a way of saying non-trivial things using some high-level language based on the free energy formula. And that's what I tried to illustrate here today. So we talked about internal model selection. Then I showed you some basic laws you can derive about phase transitions. We saw this phenomena, this non-trivial prediction about the learning coefficient rising and then falling. We talked about the fact that the transition between the overlap, the intersection of the learning curves will precede the phase transition. And this sort of idea of an emergent learning curve. These are all high school algebra. Like there's nothing difficult. Like there was no work involved in doing all of this, right? This was just free energy formula, internal model selection, and like messing around, right? Okay, so this is an advertisement for the power of the idea of having a fundamental relation, right? And then doing some basic manipulations to it. Okay, I'll stop there. Thanks. Yeah.
Yeah, it's about rocking.
Yep.
There's also something called double descent.
Yeah, I'll give it.
I don't know more of it.
I'll give a dummy's theory of double descent on Friday. that seems to be, at least in this story, is related to competition. It's competition between lambda and C. So there was no role for double descent here because basically it seems like from this point of view, I'm not saying I can explain double descent. In this framework, there is something that looks like double descent. If the overlap between the generalization errors at the intersection point here is here, then you would see that the generalization error, when it gets to here, actually this green line is above the orange line. at this point. So with the transition, the generalization error doesn't fall, it rises
Mhm.
and then falls again.
But didn't we just prove that that would never happen?
That never happens if you're ignoring the subleading term.
Ah, okay.
But if there's a subleading term, which again is consistent with the role of weight decay and data double descent, then you can and do get the reverse behavior,
So this lagging.
this lagging change in generalization.
So I'm gonna ask the next question.
Yeah.
This is all like in terms of energy and complexity, and these are very confusing words. So I'm gonna say like little anthropomorphic story, and then you can tell me what, if that makes sense. So you got all the spaces. So we start with the first dominant phase is like a simple model. And slowly we kind of get more and more info, like more and more data. And then at some point, the sort of learning machine starts to notice that this more complex phase is doing better. And one way it's doing better is it has a better generalization error. And then at the second critical point, it actually switches to this new, more complex phase.
Well, like the learning process doesn't care about generalization error. That's a derived quantity. So
Right, okay.
the model's not trying to optimize that. It's
Right,
just
okay.
an accident.
Sure, but in my anthropomorphic story, it's been chugging along. It's been doing pretty well. Like all these like benchmarks, it's been doing quite well. And then I don't know.
Well, in your story, the model wanted to switch. I don't know, because there was a generalization. So I'm going along with the anthropomorphic generalization. I just don't think it.
Right.
This is an
Well,
The question about, you would call it, suppose energy is the same.
Yep.
What's the two phases? And the learning coefficient is the same.
Uh-huh.
Two phases. Do we know anything about
Well, then
transitions in life?
once that happened, there would be no transitions. It would just instantly go to the lowest value of the subleading term.
Is it hard to?
There are two. Oh, you mean like the log n term and yeah, well, there's probably like 300 terms there, and there will be competition all the way down. So that's right. I mean, once you hit the lowest RLCT, maybe there's like some very sophisticated algebraic geometry based argument for it then transitioning to simplify some other birational invariant or something, right? So it just keeps going on. I don't know like when it stops. But I mean, it may be unobservable in some sense because you maybe need to get to n. I mean, maybe you need to be running your learning machine on a Dyson sphere to see competition between the fifth and sixth order, which, according to Jesse's talk yesterday, will be happening, anytime now. So we'll find out. Yeah, that's right. More questions?
Do we give ourselves a break?
Yeah.
Next one?
Yeah. Yeah.